Dear students, after studying this module, you shall be able to know the importance of carboxylic and related compounds, design the synthesis of three-membered ring compounds and their derivatives, design the synthesis of four-membered ring compounds and their derivatives. Carboxylic compounds are the compounds possessing a ring composed mainly of carbon atoms. A cyclic compound, which is also known as a ring compound, possesses atoms that are connected to form a ring. When these compounds are completely saturated, they are known as acyclic compounds. These compounds resemble both aliphatic and cyclic compounds in their properties. These saturated alicyclic compounds have the general formula CnH2n, same as that of an alkene, and are isomers of alkene. They do not have double bond but possess a ring structure. The ring forming reactions are an important part of retrosynthetic analysis because a number of carboxylic compounds find their application in food, pharmaceuticals, cosmetic and material sciences. Some rings are formed very easily than the others. During the formation of rings, the study of transition state stability is a significant, and hence Baldwin formulated ring closure rules. There are three important strategies usually considered when a carbocyclic synthetic target is synthesized. Any reactants already containing a carbocycle of a required size may be used. A one bond disconnection can be used in the same way as used for the formation of chains or branched structures. A two bond disconnection can be used corresponding to a cycloaddition reaction. Let us look into the synthesis of three-membered rings. Synthesis of the most simplest cyclopropane ring structure. Retrosynthetic analysis. The disconnection or retrosynthetic analysis of cyclopropane is given here in figure. Here, a one bond disconnection approach has been utilized to a cyclopropane ring. The use of a functional group oriented approach is required. The one only difference between this disconnection and elongation of a carbon chain using same approach is that here the nucleophilic carbon and the electrophilic carbon are on the same molecule and separated by just one carbon. As can be seen here, the two nucleophilic and the electrophilic centers in the same compound separated only by a carbon. 1,3-dibromopropane is cyclized using either sodium metal, also known as Wood's coupling, or zinc metal to give cyclopropane as given in figure. 1,3-dibromopropane treated with sodium or zinc leads to the cyclization and formation of a cyclopropane ring with the elimination of sodium bromide or zinc bromide. Synthesis of cyclopropane carboxylic acid. Retrosynthetic analysis. The retrosynthetic analysis of cyclopropane carboxylic acid shown by the structure 4 is given in figure here. A one bond disconnection approach has been utilized to a cyclopropane ring. The cleavage is heterolytic in nature, leading to the nucleophilic carbon and the electrophilic carbon as shown by the structure 5. The compound 5 can be obtained from the compound 6, which can further be obtained from the compound 9 and 10 as can be seen here. In the given structure, the cleavage of the carbon-carbon bond taking place leading to the formation of the structure 9 with the two ionic centers. The bromo compound is formed, which in turn then undergoes a cleavage, tracing back the reaction to the formation of the two fragments of the acid and an ionic compound, which can be traced back to the diethyl malonate and 1,3-dibromoethane. Looking into the synthesis of the compound, the reaction sequence for the synthesis of cyclopropane carboxylic acid 4 is given in the figure in the step 1. The reaction of diethyl malonate represented by the structure 10 treated with the strong base gives a carbanion. This carbanion then reacts with 1,2-dibromomethane to give monobrominated compound 11. The further reaction of the compound 11 with the strong base like sodium ethoxide gives another carbanion number 12. The carbanion 12 then undergoes cyclization to give the cyclopropane derivative 13. The hydrolysis and decarboxylation of the cyclopropane derivative 13 in the subsequent steps leads to the formation of a target molecule, cyclopropane carboxylic acid, given by the structure number 4. Another synthetic method for the cyclopropane carboxylic acid is through ring contraction of pyrazole derivative 16. In the step 1, the activated alkene like but2-enedioic acid diethyl ester reacts with diazomethane as shown by the structure 15 and at 1 and 3 position, forming the corresponding pyrazole derivative 4,5 dihydro 3H pyrazole 3,4 dicarboxylic acid diethyl ester, given by the structure 16. This is an example of 1,3 dipolar cycloaddition reactions as represented by the figure. In the step 2, the pyrazole derivative 4,5 dihydro 3H pyrazole 3,4 dicarboxylic acid diethyl ester 16 on either photochemical or thermal decomposition loses one molecule of nitrogen and forms a cyclopropane derivative 13 as shown in the figure 6. This step is also known as nitrogen removal step. In the next step, the hydrolysis and decarboxylation of cyclopropane derivative 13 gives the target molecule, cyclopropane carboxylic acid. If the reaction is done using potassium hydroxide and platinum as a catalyst via thermal route, it is known as Kirchner cyclopropane synthesis. Coming over to the synthesis of the 4-membered rings. The 4-membered rings are difficult to make due to the strained ring angles. Sometimes the most favorable conformations of the starting materials do not cyclize to give the target molecules. Synthesis of cyclobutane carboxylic acid. Retrosynthetic analysis of the cyclobutane carboxylic acid 18 is given in figures. The disconnection of one carbon-carbon bond of the cyclobutane adjacent to the carbon attached to the carboxylic group gives the synthon 19, which further gets cleaved through another carbon-carbon bond to give the two synthons 20 and 21. The compound 1,3-dibromopropane represented by the structure 22 and diethyl malonate as represented by the structure 10 are their synthetic equivalents respectively. Synthesis. The synthesis of cyclobutane carboxylic acid 18 is given in figure. The synthesis is explained in the following steps. In the step 1, the active methylene compound diethyl malonate represented by the structure 10 reacts with the strong base sodium ethoxide to generate a carbanion. The carbanion then reacts with 1,3-dibromopropane represented by the structure 22 to give a monobrominated compound 23, which still can act as an active methylene compound. In the step 3, the base sodium ethoxide abstracts a proton from the compound 23 to generate a carbanion 24, which undergoes intramolecular cyclization to afford the cyclobutane derivative 25. The hydrolysis and subsequent decarboxylation of 25 gives the target molecule 18. Let's look into the synthesis of benzocyclobutanes. The synthetic exploration of benzocyclobutanes is important because of the diverse application of these molecules. Various methods of their synthesis are available, having their own limitations and strengths. One important method is discussed here. Let's look for the synthesis of 7-bromo bicyclo 4,2,0 octa 1,3,5 triene retrosynthetic analysis. The retrosynthetic pathway for 7-bromo bicyclo 4,2,0 octa 1,3,5 triene 26 is given in figure. The disconnections of one carbon-carbon bond of cyclobutane as shown in figure gives the synthetic equivalent compound 27. Synthesis. The synthesis of 7-bromo bicyclo 4,2,0 octa 1,3,5 trienes based on retrosynthetic pathways is given in figure and is explained as follows. In the step 1, the fluoride mediated reaction of 28 leading to 1,4 elimination to yield the compound 27. In the step 2, the cyclization of the structure 27 gives the target molecule 7-bromo bicyclo 4,2,0 octa 1,3,5 triene represented by the structure number 26. The cyclobutanes are also synthesized by inter and intramolecular 2+2 photocycloaddition reactions. For example, the intramolecular photocycloaddition of 29 gives 30. To summarize, the carboxylic compounds are the compounds possessing a ring composed mainly of carbon atoms. Baldwin formulated rules for the ring closure reactions. One bond disconnection approach has been utilized to a cyclopropane ring. 1,3-dibromopropane is cyclized using either sodium metal, also known as Woods coupling, or zinc metal to give cyclopropane. The retrosynthetic analysis and synthesis of cyclopropane carboxylic acid is discussed in the given module. The retrosynthetic analysis of the corresponding synthetic steps of cyclobutane carboxylic acid are discussed. The synthesis of 7-bromo bicyclo 4,2,0 octa 1,3,5 triene based on the retrosynthetic pathways has also been discussed.